Hi everyone, this is Darrell, and in today's video, what I hope to be able to share with you guys is the importance of question analysis. Now, whenever I go through questions with my students, I find that usually it's not a case of students not knowing their content or their concepts, but the difficulty in applying the concepts that you have learned to the actual questions that you're doing. So over here, what I have today is something that we prepare for our O-level students going for exam soon. So we usually like to do thematic revisions whereby we recap some of the more challenging questions. But what I hope to show you in today's video is whenever we approach questions, how can we break it down in a way that will allow us to solve the question and eventually come to the answer. As I always say, the method in terms of how you get to the answer is a lot more important than the answer itself in most cases because the numbers can always change. So over here, I'll be selecting a couple of questions to run through, and hopefully at the end of this video, you have a much clearer idea of how to do better question analysis. All right, so let's start with question 1 over here. When we first take a look at a question like that, the first instinct that comes out should be that we are dealing with a mole concept question. Another thing that should be quite obvious to us when we're looking at the equation is recognizing that what we're seeing here is largely gases. This means that for a mole concept question that involves gas, we will be looking at the mole ratio being equivalent to the volume ratio. That is a very important baseline to establish. Next, I want you guys to focus on the wording over here, volume of the resultant gas mixture. Another way questions like to frame this or to term this is what is the volume of remaining gas. Now, why is this portion here so important? It's because only after you recognize that, okay, there is volume of remaining gas. Okay, what are they testing me for? You can then make the conclusion that this question is actually a case of excess or limiting. Sorry. So this means that whatever you're planning to do here in your calculation, you're already expecting some of the reactants here to fully react, forming the limiting reactant, and some to have in excess. And you actually need to add the excess amount back into the final volume of remaining gas. Only then you'll get the correct answer. So how do we then proceed on to solve this question? Now, what you want to do over here, personally, I'm a big fan of rewriting out the equation because it just gives me a bit more space to work with. But I'll say what is most important for me over here is being very clear about my mole ratio. So what I like to do is I usually like to outline very clearly what my mole ratios are. Now, if there's nothing in front, it means it's a value of 1. Next, I'll make it a point to write down the starting initial amount that I have. So this is 40 and this is 60. Now, what we all need to pay attention to is that we're going to react the two gases and we need to obey the mole ratio. And if the mole ratio here is 1:2, right, you need to consider which one here would run out of faster and which one will be left in excess. Now, how do we know? This is just by throwing in numbers to see which one sticks. Let's go with a very simple frame of thinking, right? How do we solve the question? If I used all 40 cm³ of methane, I'll need twice as much oxygen. If I really reacted all 40, I would have reacted with 80 cm³ of oxygen. However, do I have 80? I don't. So what does that mean to us? It tells me that it's not possible for me to react all 40 cm³. In other words, your conclusion here is that your methane is in excess. This means your oxygen is limiting. You are expecting all of your oxygen to fully react and you'll be left with 0 cm³. Now, since the mole ratio is 1:2, when you react all 60 cm³ of oxygen, you'll be reacting with half the volume of the methane. So this means 1:2, this is 30 cm³ reacted. This means that I have 10 cm³ left in excess. Now, we are not done with the question because we still need to take into account the fact that the carbon dioxide gas here produced will also factor into the volume of the resultant mixture. So the ratio here is 1:1. Now, if I haven't made it clear enough to you, the mole ratio will form the volume ratio. So minus 30 minus 60, 1:1, right? So how much gas should I form for CO2? I should be forming 30 cm³. And since the question is asking us for the volume of the resultant gas mixture, you will take whatever that is in excess and add it with whatever gas that you have produced to get your 40 cm³. All right. And there's a couple of you here might be wondering, why do you not include water, right? So why is water not a gas? It's because you need to be very careful when you read the question. All of this is measured at room temperature and pressure. And at room temperature and pressure, water is a liquid and not a gas, as evident in your equation as well. So over here, what we have done is, I won't say a very simple, but a relatively classic mole concept question on limiting and excess. It is the wordings like this that gives it away. Volume of resultant gas mixture or volume of remaining gas. Because when you see such statement, you need to identify the question type, which is excess limiting, and then deploy the correct calculation step to get the final answer. Okay, so this is what we mean by question analysis. It's about breaking down the question instead of just blindly throwing yourself in and trying to solve it. So once again, remember, identify what's the topic, mole concept. What's the concept, excess limiting, and then you break it down to solve it step by step. Now, let's take a look at another question, for example. Over here, we see compound M. It tells us the percentage by mass of each element. So what we would want to do is to first draw it out in the form of a table. We have our sulfur, we have our oxygen. Now, the first thing you're going to put down is the mass, and we're going to put it down in exact percentages. The next thing you would want to find is mole. Now, very important question to ask ourselves is, how do we go from mass to mole? The formula is mole is equals to mass over mR. So what we need to do is to take this 40 divided by the mR in order to get the number of mole. So what you want to do over here is you want to divide by the mR of sulfur, which is 32, and you also want to divide by the mR of oxygen, which is 16. So I'm just going to take a second to key into the calculator over here. What you get is 1.25. And as for the oxygen, what you're going to get is a value of 3.75. At this point in time, you're not done, because it's very important for you to recognize that the final step is actually to determine our mole ratio. And over here, you can quite clearly see from a mathematical perspective, the mole ratio is 1:3, which means, therefore, for every 1 sulfur, you have 3 oxygen. Okay, so once again, when we do this question, it's not about just jumping straight in, but recognizing that the way to solve the question is by putting it in the form of a table. This is quite similar to how when you find an empirical formula or eventually to find a molecular formula as well. So I just need everybody to be on the same page with me whenever we say question analysis. How do we break down the question and what is the correct approach? So let me show you a couple more questions to look at, and we can think through what is the key thing here. When we are reading this question, there should be a very heavy emphasis placed on the fact that the y-axis is your pH. All right. And we are looking across the board. How does the pH change according to the different oxides that I'm forming? So what you need to think back here is, which chapter is this about? The biggest clue that gave it away is the word oxides of elements. And when do we learn about oxides? Is in the chapter acid and bases. Specifically, there are 4 types of oxides. There's your basic, amphoteric, acidic, as well as your neutral oxides. So what I want you all to take a close look at here is that we will categorize metal oxides like your sodium oxide and your magnesium oxide as basic oxide. And basic oxides here will have a very high pH. And as we go through, we will see that aluminium here is one of the amphoteric oxides that you have learned. And last but not least, I want you all to pay attention to how these remaining portions of oxides are your non-metal oxides forming acidic oxides. So you can quite clearly see how the pH will be dropping over time, as you initially started with something that's more alkaline in nature, they are basic, proceeding on to form acidic oxides from here onwards, because they are non-metal oxides. So by looking at the keyword here, oxides of elements, during your question analysis, you can already get a sensing of what they're testing you for, whether you know what happens when these oxides dissolve in water. Okay, so that's why question analysis is extremely important, because it helps you guide you to the process of identifying the correct topic and the correct concept. So let's take a look at question 4 next. Which pair could 2 substances be distinguished from each other via visual observation? Now, visual observation here is very important because it means that the reaction must produce some version of something you can see. Now, visual observations are usually in a few parts. What is obvious at most visual observations is gas being produced, all right? Or you can have a precipitate form, or your solution changes color. One way I like to categorize and think about this is solid, liquid, gas. So will you see any solid? Are there any precipitate forming? Your liquid, is it changing color? And for your gas, is there any effervescence observed? So when it goes to visual observations or state any observations, you can always think in terms of solid, liquid, gas. Are there any things that you will see specifically? Now, let's take a closer look at such options that are being provided. The first one I'll be looking for is with gas. Acid can actually react with metal and carboxylic acids, carbonates to produce gas. However, none of the options are actually available in the table. So this is not a question about producing gas. Now, what about color changes? Neither observations will likely result in any color change, which means by process of elimination, we are likely looking for a situation whereby a precipitate is formed. Now, this chapter itself, if you take a close look, is actually a chapter in salts. You can also argue it is part of your QA, but those two chapters are closely related anyway. But what I need you to know over here is this. When you're looking at the two pairing, the nitrate is the same. Therefore, it's not the nitrate that will result in any difference. If anything, it is actually the cation that's responsible. And what do I need you to be able to recognize when we say lead-2 and sulfuric acid? Lead-2 is Pb2 plus, sulfuric acid is SO42 minus. I need you to be able to recognize when these two ions come in contact or when they are placed together, precipitation happens as lead sulfate is an insoluble salt. Therefore, when you add sulfuric acid to lead-2 nitrate, you will actually get a white precipitate. This goes back down to whether you know your insoluble salts and your soluble salts. So whenever you have two ions coming together to form an insoluble salt, this process is known as precipitation. So by visual observation, the point that was met is that a precipitate will form, allowing you to identify which substance here is the lead nitrate, while the sodium nitrate will not give you any visible change. So the visual observation is actually the clue, the question analysis that you need to be able to do in order to get closer to the answer itself. Okay, of course, there still needs to be some level of content mastery for you to solve such questions, right? So it's not something that you can do from scratch. You still need to study first, but the question analysis is very important. And this is not a process that you want to rush through. Next, let's read through question 5. The student recorded the observation. There's no fizzing, right? So there's no gas. Solution changes color. This means that your solution itself, something took place. Next, no precipitate is formed. Once again, going back down to question analysis, it's always about solid, liquid, gas, isn't it? And here, the key thing that we're focusing on is that the solution changes color. So what did the student mix? Over here, we have dilute sulfuric acid and copper 2 oxide. If this is a question, I will highly recommend writing out the full balance equation for all the options. But in the interest of time, I'll only go through the correct answer for today. So sulfuric acid is H2SO4. Copper 2 oxide is CuO. Now, what do I need you guys to know here? You need to be able to recognize when we are pairing reactants together and there are observations. This means a chemical reaction has taken place. And in this case, what you need to be able to do is to recognize that this is an acid and this is a base. In other words, a neutralization reaction should have taken place. And when acid is reacted with base in a neutralization reaction, what you'll form is your salt plus water. And what you need to also recognize here is that your salt form being copper sulfate is a soluble salt in aqueous state. Therefore, in its solution form, it will be floating around as copper 2 plus and SO42 minus. Now, the last bit that you need to stitch it all together is why is there a change in color? It's because originally it was colorless, with copper 2 plus now floating in the solution upon reaction. The copper 2 plus will have a blue solution. So in other words, when looking at this question, what is the question analysis? How should you be thinking of the question is this? If I'm given two reactants and they clearly told me that something has happened, the trick is actually to write down for each equation what the exact reaction is. Sometimes there is a reaction, sometimes there isn't. And if it helps, writing down the chemical equation could shed a lot of light. and help you come closer to the question answer itself. Okay, so there is no fixed way per se, but it's just how you open your perspective when it comes to solving question. The unfortunate truth is this: the more you do, the better you get at it. But there needs to be a conscious effort in terms of analyzing the question, understanding what they're asking for first before you solve it. Next, let's take a look at our group 17 elements starting from chlorine to iodine. All right, and they are telling us the property is this: iodine has the largest value, chlorine has the smallest. So let's look through each of these points one by one. What they're testing for here can be summed up to this: which chapter they are testing us on our ability to recall the trends in the periodic table chapter, specifically for halogens. So you want to bring all of your knowledge and your focus to, okay, in group 17, what are the trends that I know? Now, as we take a look at this tree, what you should know according to your syllabus is chlorine exists as a yellow-green gas, bromine as a liquid that is reddish-brown, and iodine as a black solid. So among this three, right, it's quite clear if iodine is a solid at room temperature and pressure, it will have the highest boiling point. And something that is the heaviest will have the largest density as well. So 2 and 3 is almost confirmed. Therefore, when we look at the options, you should be narrowing down to either C or D. So the only thing left is to determine is oxidizing power. Now, oxidizing power itself might be very intimidating if you think, oh, does this mean I need to link back to oxidation and reduction? There's actually a very simple way out if you actually know your stuff, which is that oxidizing power can be more simply interpreted as reactivity. What do I mean? Typically, something that is more reactive will have a stronger oxidizing power. That's it. In other words, is iodine more reactive than bromine? Is bromine more reactive than chlorine? The answer is no. Because at the end of the day, you need to remember that fluorine is the most reactive in group 17 and reactivity decreases down the group. All right, and that's how you actually approach the question, by recognizing that they are testing you on trends in the periodic table, subsequently by looking at each pointer and understanding how they are related. All right, density and boiling point are related to physical properties. So usually when boiling point increase, generally, sweeping statement, density will increase because all physical properties would follow a trend. But for oxidizing power itself, it's talking about reactivity. So it doesn't necessarily follow the same trend as your physical properties. Let me move on to the next. Over here, we are shown that bromine is being added and is being shaken with sodium chloride and sodium iodide. I think what we need to be very clear here is that whenever you see two near identical ones, but the only difference here is chloride versus iodide, it needs to trigger a little bit of awareness here. Why am I adding bromine to these two solutions? And that is when you come to conclusion that by analyzing the question, bromine, chloride, iodide. Where are we going with this? It is still the chapter of periodic table. And the concept they are testing for is no longer the trend for its properties, but whether you know a case of displacement. Whether you know that the more reactive will displace the less reactive. So how would the final solution look like? You need to understand that bromine is unable to displace the chloride as it is less reactive. But bromine can displace the iodine as bromine is more reactive than iodine. Therefore, when bromine is added to sodium iodide, what's going to happen is that it will form sodium bromide plus I2. So that's the reason why in your final answer, you must have iodine present. Okay, and that's also the reason why we have sodium bromide. Meanwhile, the sodium chloride is left untouched. Therefore, these are the three things in your final solution. All right, so always think back, because everything that you'll be tested links back to a certain thing that you have learned in your syllabus. It is within a chapter, there's a specific concept. So a lot of times it's about first using these clues to narrow down what they are testing you for so that you can apply the correct solution to solve the question. All right, if not, let's push on to just do a couple more questions so that you can get the hang of things. Now, for question 8, the wording here, rusting, immediately gives it away. So the question is asking, how does spraying the steel bodies with zinc help to prevent rusting? Let's go through the statements one by one. Now, would zinc form a stable compound with iron? It will not, because we are both looking at metals. Metals do not form a stable compound with one another. If anything, the word here is that it can form a mixture. It could have technically formed an alloy, but a compound means that chemically reacted. Metals don't react with metal. So we have already eliminated option 1, which means B cannot be the answer. Next, zinc would form a physical barrier from air and water. Now, is this true? Yes, it's because zinc is more reactive than iron. So that is one of the more important things that you need to recognize here based on how you have remembered your reactivity series, either via mnemonics or song. I don't really care. But the main point is that zinc is more reactive than the iron that's present in steel. Okay, so this statement here is true. Next, zinc does not react with the acidic exhaust film. Now, this statement itself, even if you're not too certain, I would say that the main focus here is, will zinc react with acidic exhaust film? Now, acidic exhaust film themselves doesn't react directly with metal. If anything, it is true that acid react with metal, but acidic films are not yet acidic until they dissolve in water. So here, this statement is therefore not true. Lastly, we can all agree that your zinc is higher in reactivity than iron. And this is the reason why it will react in place of the iron. So in other words, that's how it forms a protection from rusting itself. So your zinc will react in place of your iron. Okay, let's move on. Last 2 questions before I wrap this video up. We were told that your potassium iodide is added to an unknown substance and the substance turns brown. Now, what is being tested here, you might be surprised, is actually no longer your reactivity series or your periodic table. The question has already moved on. Now, when we take a look at this wording here, potassium iodide, if you studied well enough, you will know that Ki is actually your reducing agent. And this reducing agent itself will turn from colorless to brown. And when does it do so? It turns from colorless to brown when the reducing agent undergoes a redox reaction with a oxidizing agent. That's all. All right, so your reducing agent will only be activated when it's paired with an oxidizing agent. So this question is more of recognizing when you see the word potassium iodide, it's a dead giveaway that is a reducing agent. The good news is that there's actually only one reducing agent that you must memorize or must know in detail, and that is potassium iodide. The equivalent for oxidizing agent is your acidified potassium manganate. Those are the two whereby you need to know them by heart. You will also need to know their color changes. Lastly, let's take a look at question 10. Typically, electrolysis is always a question that scares a lot of students, but how I like to break it down is in 3 parts. Whenever you do a electrolysis question, you need to analyze a few things. The first thing is to analyze, firstly, what type of electrodes are being used. And when you see platinum electrodes, I need you to have the understanding that this is inert. Other than platinum, it could be carbon, it could be graphite for all that matters. But as long as you're dealing with inert electrodes, the electrodes itself will not directly dissolve and take part in the reaction. So this means we are looking at largely 3 possibilities: molten, aqueous, and concentrated solutions. Next, we were also told a very big clue, which is that it produces bubbles of gas at both electrodes, meaning both electrodes itself must give you some version of a gas. Now, the last level of analysis is, okay, so the first one is the electrode. We also look at the product. And the final one that we need to focus on is actually what are the ions present in the solution. So let's take a look at the correct answer first. Aqueous means it's dissolved in water, which means there is H plus, there is OH minus. Sodium chloride over here means there's Na plus, and there's Cl minus. Therefore, what you need to do here is to apply your concept on ease of discharge and recognize that between H plus and Na plus, H plus will be discharged. And between OH minus and Cl minus, OH minus will be discharged. And once you can do this, actually the question is pretty much done. Because what does H plus form? It forms hydrogen gas. OH here would form oxygen. And that's why you get bubbles of the 2 gas produced at both electrodes. So when it comes to electrolysis question, it's not about just jumping the gun, but looking at a couple of things. Looking at firstly, is your electrode inert or non-inert, right? If it's reactive, the anode will dissolve. Second, you want to focus on, firstly, if they mention anything about the ions in the solution, because if that happens, you can have a much clearer idea of what are the ions present and therefore what will be selectively discharged. The last thing that we usually look for is the products that are being formed. So that will help guide you in terms of thinking what has happened in this solution. So in general, when it comes to electrolysis question, the analysis and the breakdown is more important than the actual answer itself. Because over here, if the question changes and they say, oh, I only produce one gas at the anode or the cathode, then definitely it will be a different set of analysis. But the way to do the question is still the same. All right. And with that, I hope that this video was helpful in terms of helping you understand a little bit more on how we do question analysis. Of course, there's so much more topics, so much more questions. So I cannot be going through anything, but at least let me sit you with the thought on when you're doing questions, there needs to be a very systemized way to think about the question. Identify the topic, then identify what is the concept in the topic. And then when you're doing the question, there should be a most efficient way of breaking it down and therefore getting you to the final answer. So always focus on the way and how you get the answer rather than the answer itself, because the answer can always change. And the more practices you do, the naturally you get better at it. And I'll say at the end of the day, if you do want to master chemistry, physics, or even any other subjects for that matter, the question analysis is very important as that will guide your entire thinking process. So I hope today's video was helpful. If you enjoyed today's video and you would want more of such content, do let us know so that we can actually get them out so that you can use them for your own revision and sessions. To learn more content, learn more knowledge, we are more than happy to share. But let us know in the comments below what else you would like to see next and if this kind of videos are what you're looking forward to. If not, that's all, and I wish you all the best for your revisions. Signing off.